Okay, so welcome back for this morning, last talk of this morning session. It's a pleasure to welcome Francis Bach from INRIA Paris, who will speak about, I guess, submodular function and discrete and continuous settings.
Okay, thank you, Gabriel, for the introduction and for inviting me here. It was a pleasure to talk at IHP, in particular in a very cool day like today. So before I start, I'll do a small survey. Who has seen at least once what a submodular function is? Submodular. Okay, good. Okay, so let's say 20%. So the goal of today is I will try to cater to both audiences, people that know about submodularity and people that don't, and hopefully all of you will get something out of it. So the key today is to consider optimization and what function can be minimized in polynomial time. And as Anders has started to show, you need to be able to optimize what you propose. It's not simply a matter of proposing a cost function. You have to make sure you can optimize it. And today we're going to look at situations where we want to define a whole class of functions which we can minimize in a polynomial time, regardless of further assumptions. So it's a bit different from compressed sensing. For example, what he showed already, that if you have a L0 penalty, then you may optimize in a polynomial time if you make some assumptions on the design matrix, like our IP assumptions. What I'm going to discuss today is a bit different. I want to design a whole class of functions, like convex functions, for example, on which you know in advance, and regardless of assumptions on your data, that you can optimize in a polynomial time. Of course, you know that convex functions are instances of that kind. And this is something which I'm going to use a lot today. So there is another class which also leads to algorithms in a polynomial time, is so-called submodular functions. So those are functions typically defined on the hypercube. Those are often called set functions. And as I will show today, this is in fact, they are equivalent to convex functions. You can represent them in a convex way, which makes them amenable to convex optimization. And what I will try to do today is to show that all those concepts which were created for the binary hypercube can be extended to vector spaces. And this will be done through no line of proof, just using existing results from optimal transport. So if you want to know more, you can look at the preprint. Okay, so submodularity, whether you know it or not, you have been already using it quite a bit because it comes up in many places. Let's take clustering. So you have data like this, like in 2D, and you know that the red dot should be in one class, the black dot should be a second class, and you want to classify the rest of the dots. And this can be seen as an instance of submodular function minimization, and I will explain which function I mean by that in a moment. Okay, so this, whenever you do semi-supervised clustering, you're doing, in fact, submodular function minimization. And a classical example of that is when you do graph segmentation. So if you ever used the lasso from Adobe, not the lasso from Tipshirani, then you have done something like that. Okay, you give an image, like a nice dog like this, and you say, I want to segment the dog outside of the foreground, and you put a few strokes, and you let the method finish for you. This is exactly the same problem as the slide before. Submodular function minimization, and here this is a cut function which you're going to minimize. Okay, so you're already using it every day. Then you may want also to maximize submodular function, and this I will not cover this at all in this talk, but this is a usual sensor placement problem. You have a city, like American city with a square grid, and you want to put antennas. Each antenna has some coverage. And the goal is you want to maximize the coverage while minimizing the number of antennas. And this is an instance of submodular function maximization, which I will not cover at all today. But you have to keep in mind that whenever you mention submodularity, it comes up either in maximizing, where algorithms do not have polynomial time and do have some guarantees, and minimizing, where essentially we can minimize exactly. And finally, and this was already mentioned by Anders, this is the variation problems. So whenever you want to add some structure into your sparsity-inducing norm, you want to go beyond imposing a maximal number of zeros, then you need to put some discrete structure somewhere. in the context of images, you want to impose the fact that images are piecewise constant. And this can be seen as, so submodularity is not obvious here. There is no like binary function which you want to optimize. But as I will show briefly, you can use submodularity to design things like this. And essentially, total variation will be essentially the convex extension, which I will use a lot in this talk. All right, so this is it for example. So let's now get down to so the usual notations for submodularity. You have a set V from 1 to n. We optimize over the power set to the V, which has like 2 to the n element. And the problem of minimization maximization is minimizing over all subsets of A. And here, since we are in France, including means potentially equal. Okay, so yeah, so A is inside of V or equal to V. So this is the usual like way of formulating, but in this talk, I will prefer to use a binary hypercube formulation, which is like in one-to-one correspondence with the set functions, and you can go from subsets to any vertex of the binary hypercube by considering the indicator vectors. So this is very trivial reformulation, and I will focus mostly today on that binary hypercube. So every vertex of the binary hypercube corresponds to a certain subset, and I'm going to consider mostly that problem. I want to minimize over x in 0, 1 to the n h of x. Okay, so this is, I'm showing this slide because most of the references on submodular functions are using that notation, just to make things clear that they are totally equivalent to each other. All right, so this is the outline for this morning. So I will first define like the usual concepts for submodular set functions. This will be mostly a review. Then I will show that essentially everything goes through for when you go from discrete to continuous. And then I will show some like how you can minimize those functions in polynomial time. All right, so before a bit of shameless promotion. So if you want to know more about submodular functions, you have a nice book by Fujishige, which is where the starting point is more combinatorial optimization. So if you're more from like discrete math, computer science, this may be a good one for you. But if you're like me and you come from like convex optimization, this is a better reference where starting from convex optimization, all concepts are derived, and most of what I will describe today for the first part is contained in that book, which is free, by the way, online. All right, so definition. So what is submodularity? So I'm considering a function on the binary hypercube, or defined on all possible subsets of a given set. And this is going to be submodular if this equality is satisfied. And just to parse this equality, x represents a set, okay? Y represents a set. The max of xy, where the max is taken component-wise, corresponds to the union of those two sets. If you take the max of two indicator vectors, you get the indicator vector of the union. And this is so the union of the sets described by x and y, and the minimum is the intersection of the set represented by x and y. So what this said is said that the value at a set plus the value at another set is greater than the value at the union plus the value at the intersection. So if you have an additive measure, you have an equality sign over there. Okay, so this is the usual like property of additive measures, and to be submodular, you only need to have this inequality over there. So when you have an equality, it's called a modular function, and this will occur quite a bit in this talk. So this is not usually the easiest one to understand. The easiest one is this equivalent definition, which says that if you fix a node I, okay, and you consider the effect of adding I to your existing set, okay, so you have an X, you add I, so you get X plus EI, so it's adding an element in the set, then you make some progress, so you have a difference in gains, and this has to be non-increasing. So this is typically used, so if, for example, so we're going to drink a lot today because it's hot, so the effect of the first glass of water is very high. If H is your like happiness level, H will be very big if you add like one more glass of water. But if you add like one glass of water on top of already like 5 glasses of water, the gain in happiness is not that great. Okay, so this is just showing that the happiness of drinking water is submodular. Okay, this applies to beer, wine, and so on. And with anyway, so yeah, so this is just the usual like other definition, which is this diminishing return property, which should make you think about a concave property. Concave functions on the real line have this diminishing return property, and this is essentially the equivalent for set functions. Okay, so diminishing return property. So a few examples. First, we'll see like a few. So concave functions of the cardinality are indeed submodular. So they just enhance the fact that there is a bit of concavity when you play with submodular functions. Cuts will be examples, entropies, and various like functions of eigenvalues. And let me jump straight to the concave functions of a cardinality. So if you take a modular function, so this is a function which is both modular and supermodular, and those functions happens to be linear functions of the indicator vector. Okay, so this is like, you can convince yourselves of that rather quickly, is that these will be functions which are modular. And if you take W here, the vector to be a constant vector, you get a cardinality associated with the cardinal with the set represented by X. What this says is that if you have a concave function of cardinality, then it is submodular, and the proof is two-line. Okay, so it's just an example of simple functions which are indeed submodular. Then you have the famous, like for the sensor placement, so covers. So now this may look a bit contra at the beginning, but so you have a set V, which is indexing your possible antennas. And for each antenna indexed by K, you have the set SK, which is a coverage area surface of your antenna. And if you define, like given a certain number of antennas, okay, defined by X, if you take the union of all the areas indexed by X, then you get a set like here in 2D, and then you take any additive measure of that set, and you get a submodular function. So here it's obvious this is submodular because adding an antenna when you already have a lot of antennas doesn't bring as much new coverage as if you had only a small number of antennas. Okay, so this one is submodular and used a lot in practice, in particular for those coverage problems. Second example is a cut. So this is like the one that we use to do like the Adobe lasso. So you have a graph which could be directed or undirected, and you select X. You look at all the edges going from the set indexed by X to the others, and this is cutting some edges, and the cut is simply the number of edges which are cut, and this can be generalized to weighted graphs. And essentially, for the image problem, each node represents a pixel, and the goal is you want to minimize the cut, so you want to have zones which are as flat as possible with only a small number of cutted edges, and this is essentially what people use for cuts. Okay, now so there are other examples. So if you like eigenvalues, and you have a full class about like random matrices by INRIA later on, then you can show that some functions of eigenvalues are also submodular. All right, so what we're going to do, we want to go from discrete sets to the binary hypercube to the full hypercube. So there's a tool for this, which is called the Choquet integral, okay, often called the Lovász extension. And this can be defined for all functions. Give me any functions defined on the vertices of the hypercube. So at every red point, you can always cut the full hypercube in simplices. Okay, so this is like a small tetrahedra. And all of those are defined by a particular ordering of your nodes. Okay, so you can, any cube, so here in dimension 3, can be cut into 6 pieces, depending on the 6 possible ordering of your 3 values. And then once you are in one of those tetrahedra, or simplices in higher dimensions, then you know the value at every vertex of that tetrahedra, and you want to, then you can linearly interpolate within that tetrahedra. Okay, to do interpolation, a fine interpolation, you need just like d plus 1, you need d plus 1 by n plus 1 here values. And this is how the Choquet integral is defined. For each of those like pieces, just do linear interpolation, and this defines a function on the full hypercube, which is named the Choquet integral. It has a certain formula, okay, and the formula is totally irrelevant. I just put it there to show that it is very simple. But if you want to interpolate like among like those 4 values, 1, 2, 3, and 4 for this that simplex, then you end up doing a formula of that kind. And again, the formula itself is quite irrelevant. What is important is that you get a piecewise affine interpolation. And because h of 0 is always 0, it is a piecewise linear interpolation. Okay, so this is the way we can achieve like extension from the vertices of the hypercube to the full hypercube. All right, so let's look at some examples. So if you start from a linear function, okay, like a modular function, so a linear function of your binary vector, then linear interpolation will give you just the same function. So the extension, which I will call small h of mu, is just the same linear function. Now, if you take the cut, you can show that for the cut, the extension is now the so-called total variation on the graph. Okay, you sum over all edges in your graph of the deviation between the value at k, the value at j, and take the absolute value. This is exactly the total variation of the graph. So hence, the link between like those structure sparsity applications and submodularity. You can see many of the regularizers used in signal processing or machine learning as being the low-pass extension of a given submodular function. This is not what I'm going to do a lot here today, but this link allows you to get a lot of interesting both algorithms and analysis, but I won't cover it today. I will cover mostly the optimization part today. All right, so what are the properties of that set function? So by design, it is a piecewise linear because doing linear interpolation. It is positively homogeneous. It's not obvious, but because this is due to the fact that h of 0 is 0. And by design, it is an extension. If I take the value at any element of any of the vertices of the hypercube, you get the exact same value because it's just by design. Okay, so this is essentially the extension. So again, this can be defined for any function. Give me any set function. You can always design such a set function. It's easy to compute. Okay, give me any vector mu in Rn. Then you can order the components. Okay, and then you get like this simple formula. So here I've made the switch from the hypercube, the interval 0, 1 to the end, to the full Rn. I'm going from there to there. And so the way it is done is that you define this only for elements in 0, 1 to the n, and you use the same formula for the full vector space. All right, so now let's look at some properties. And here I'm summarizing like 30 years of submodularity, and this dates back from Lovas in 82. And what he showed is the following, is that this extension which I've defined earlier on is convex if and only if the function you started from is submodular. Okay, so this is like an if and only if. And if you look at the total variation example, it's just not a proof, but it's just an illustration that we started from a cut, which is submodular, and we ended up with a total variation, which is convex. Okay, so this shows that whenever you do some submodularity, you happen to do also some convexity. But even better, he showed that if you want to minimize your submodular function, so you minimize over the vertices of the hypercube, by design, this is equal to that. Why? Because small h is an extension of capital H. So if you minimize on the vertices, this is like the same. So this equality is always true. This one is much better because it says that instead of minimizing your function on the vertices, you can minimize on the full set. And now what you obtain is the minimization of a convex function, h, when you're submodular, over a convex set. So this is already like starting to look good because you have convex optimization, but you need a bit more. You need to be able to know a bit about those like convex set and convex function. So that set is easy to project to, so this is very simple. But that function h, it may be convex, but it may be very hard to minimize because you have no access to a subgradient or anything like this. But it turns out that you have access to a subgradient simply by realizing that locally you have a linear function of mu. Okay, so it doesn't take long to notice that this will define the subgradient of your function at any point. Okay? So this is essentially what's happening. For any mu, you can simply get a subgradient by ordering all components of mu and doing some functional evaluations. Okay? So this is a summary of like 20 years of submodularity. And the key is that now you have transformed your submodular minimization problem into a convex optimization problem on which you can do many things. All right, so now let's know, so the consequences, and this is the first consequence. The first consequence is that you can minimize that problem in a polynomial time, and for example, using the ellipsoid method, which is a simple way to optimize any convex function for which you know a subgradient. Okay, so this just shows that from the start, you can minimize those functions in polynomial time, but of course 5 is a bit big because you have to imagine that in the graph cut example for images, n is a few millions. Okay, so a few millions power 5 is not really usable. All right, so what people have designed several types of algorithms for that problem. The first one is, so the way all the algorithms always work in the same way. They use this convex formulation and just try to find a good mu and also a dual certificate, which I don't want to get into today, to prove optimality. And this is done in two ways, either by using like so-called combinatorial algorithms, which are very similar to max flow techniques. So all techniques that you know for the maximum flow problem, like push, reliable, scaling, and so on, can be reused in that setup. And they get like per time complexity, but the best is n to the 6 at the moment. Okay, so this is totally not usable and not used at all, because this is like really a problem. Okay, so this is where it may be good to see this as a convex problem, and this is what people have been doing in the last few years. So we consider that problem. So and what do we know about that problem? We know several things. H is convex. Okay, it is a polyhedral function, like the level sets are polyhedral, and we know subgradients. Okay, and so now we can turn to our like optimization friends, and what are the techniques which can be used on such a problem? Okay, I have a convex function of a convex set, and so then you can use any of the algorithms, and those algorithms are totally blind to the submodular structure. Once you know how to do this, whether it comes from a submodular problem or not, doesn't really matter. So you can use like any trick in the book, and you can use like subgradient, Frank rules, simplex, cutting planes. You can use anything that you like on that problem, in that problem. And if you want to know more, you can look at my monograph that will tell you a lot about like various things. So here we escape this like high power in N because we use like very simple first order techniques to minimize. And if you want to know more, really do look at the book. But the goal of today is to try to go beyond that setup. Okay. Any questions so far on like the binary submodularity? All right, so now let's look at the how to extend this to like all possible functions. And this will come essentially with one big insight. And this is that the set 0, 1 is totally ordered. So I'm sure you believe this. You were all aware of it when you entered that room. But personally, I hadn't like realized that this was the reason why submodularity was so tightly linked with convexity. This was because of this. Okay, the fact that 0, 1 is totally ordered. And my goal in the next 20 minutes is to show that this is indeed the case. The only thing that we need is the fact that we have a totally ordered set. And the way to do it is by extending it to more general, totally ordered set. Okay, and so let's first look at the first extension when you go from 0, 1 to the set with k elements, not only 2, from 0 to k minus 1. And you can define submodular functions in exactly the same way by taking x in that set, taking hy and taking the pointwise minimum there, pointwise maximum over there, and you get the exact same definition. Okay, so this is simply, so why can you define this? Because to be able to take the mean of two elements, total order is typically a good thing. Same thing for the max. Okay, so you need to be able to define the mean and the max, and when you're totally ordered, this is always possible. And then you can other definition, which I'm going to use immediately, that if you take x and y being just like two components apart, then you have the exact same definition where if you add an I to x and add a j to x, then it is more than adding two at the same time. Okay, you get a similar notion of diminishing returns. And if you want to know more, there's a nice paper by Topkis doing this. And now let's see. The goal is to continuous. Okay, we want to go from not only k elements but to like a continuum of elements. So what we're going to do, we're going to do a Taylor expansion of this around x. Okay, so let's assume that EI in fact has a very small magnitude and do a Taylor expansion. So let's do a Taylor expansion of that sum. So in black, this is the first order term, the 0th order term. So you get one from this, one from that, one from there. In blue, this is the first order term, so gradients. So gradients times 1 because this is like a unit vector. Same thing, gradients with respect to j times 1. And then this is the second order term with Hessians, okay? And this one comes from the first function, and this one comes from the second function. So this is for the left part. I can do the right part, and I get the exact same thing. I get 0th order term, they match. First order term, they match as well. And now if I expand the second order term of this one, then I get like those three elements because I get like the square of EI plus EG, EI plus EJ. And now if I subtract, because I want to have this greater than this, then I get a single term which is like arriving in that this one. So essentially, the take-home message there is if you want to go beyond like discrete sets, what all those properties which looked complicated ends up being equivalent to partial derivatives being negative. Okay, so this is now the way I'm going to define submodular functions. This is simply whenever you have like totally ordered set, and here I'm going to assume that I have like interval because it's simpler to define derivatives, then your submodular if only if the derivatives, the cross derivatives are all non-positive, and this is for all I different from j. Okay, this doesn't tell you anything about the second order derivative with respect to I. So here you cannot take j equal to I. You have to have I different from j. So this is from now on, what I'm going to consider are functions which are have that property. So let's do that. Okay. So first, let's look at the usual properties of those functions. Okay. So like in convex functions, what is nice about convexity is that you can go from a convex function and derive new convex functions by simple manipulations. And the simplest manipulations for convex functions is like addition. If I add convex functions, I get a convex function. So the convex functions form a cone. This is the same thing for submodular function. So if you take two functions h and g, which are submodular, their sum is also submodular. So this is also very, very simple. Same thing for convex functions. The class is invariant by affine mapping. So if you take h and replace h by h of ax, and a is a linear map or affine map, then it is still convex. So here the equivalent for submodularity is if you take any set of functions, phi1 to phi n, which are strictly increasing. Okay, so you modify each variable with a bijection, essentially, which is like an increasing bijection. Then you remain submodular. And the proof is trivial because if you just apply the chain rule on that, and you replace xi by phi of xi and xj by phi j of xj, you simply multiply by the derivatives of phi I and phi j, which are assumed to be positive. So essentially, you don't change anything by doing this. So this is like a nice way of doing some invariances like that. And finally, what is the equivalent of linear functions? So for convex functions, those were functions which were both like concave and convex. Okay. For us, this would be the modular functions, and for the binary set, this was like linear functions of the indicator vector. But now, these would be functions which are called separable, which are sum of functions that depend only on a single variable. Okay. So now, those ones are submodular, which is totally obvious because if you take any second order derivative with two different components, they will all be equal to 0. Okay, so here, this is really one key aspect that set is huge. Okay, that set contains a lot of functions because any variable you can have any function. It can be anything, convex, non-convex, concave, non-concave, a bit anything. So a few examples. So first, the trivial one. So quadratic functions, of course, are submodular if only if the Hessians have non-negative of diagonal elements. This is just like stating the definition. And interestingly, if you know about like convex relaxations, those are quadratic functions on which the SDP relaxations are tight. Okay, so it's a nice note that there is a link between like SDP relaxations that INRIA made mention at one point and those functions. Then more interesting, any convex function of the difference. Okay, so if you take any convex function of phi and take the difference of two values like this, you get a convex function which is also submodular. So this is an example of a function which is both convex and submodular. But if you take the next one, if you take any concave function of the sum, this is a concave function, but it is also submodular. So you can see that convexity and submodularity have nothing to do with each other. Okay, so one you can be submodular and convex, submodular and concave. Nothing is so related. The log det is also submodular. So you have a bunch of functions which are submodular, and they have names. So that's why it's not a really new class of function. This is like well known. And depending on the community, if you work in economics, it's more like Spence-Mirrlees condition, and Guillaume Carrier calls that monotone of order 2. Okay. Let's give an example in 2D to see how nasty they can be. So this is a function. So those are the level sets of a function defined on R2, which is submodular. So why is it submodular? Because I have a submodular term, because this is the convex function of the difference of two values. So this is submodular. This is separable, only depends on x1, x2, x2. So you can see that that function may look quite difficult, because locally, if you look at the local behavior, you have some local maximum, you have some stationary points, you have some local minima, okay, and you have a global minimum. Okay, so if I give you that function and I tell you that I can minimize this like very easily, you would be surprised. And here, so the structure that we are going to use is not really a local structure. This is going to be a bit different. But that type of function can be minimized. And the reason why is because you have this submodular term over there. This is just to highlight the fact that that class of submodular function is rather different from convexity. You may have local minima and local maxima, but you can still like minimize. All right, so how are we going to do it? We're going to follow the exact same route as we did before. So in the binary case, we started from the hypercube, went to the full cube, and went from a submodular function to a convex function, which was a Lovász extension. And we're going to do the same. Okay, so this is essentially the summary of what I've presented earlier. You have the Lovász extension, take any mu in the full cube, out of the components, and then do that formula. And if you do a simple like Abel summation trick, you can rewrite this in the following form, okay, as a sum of differences between things like this and of values of the function, okay. And if you look really carefully, then if now you take a uniform variable t, uniform in 0, 1, okay, and you look essentially whenever t is above or below the values mu1 to mu(n), okay, so this will give you like some indices which are bigger than t, and you compute the expectation of that function, okay, and then you can see that you recover exactly what I have above. So why? Because to be exactly like, you first have to order all the components, which you do, and you're going to be that set, okay, if like mu jk is bigger than t, and jk plus 1 is smaller than t, okay, you have to hit exactly between mu of jk and mu of jk plus 1, and the probability that you hit that interval is exactly that value. Okay, so this is I'm going to generalize this like in a moment, but this is just a simple way to see the submodular extension. Okay, and now this is the way we're going to extend it, is to realize that when we went from the hypercube to the full cube, what we did was to go from the set 0, 1 to the set of distributions on the set 0, 1. Okay, that distributions on the two values 0, 1 are defined by the probability of 1, which is a number between 0 and 1. And this is what we did. We did simply something like that. We define like product measures. For any I, we define mu I, a real number coding the probability of being 1 or 0. And that number is, in fact, and this will become like more clearly in the next slide, we simply took the inverse cumulative distribution function. Okay, so this is just to highlight the fact that what we did in the case 0, 1, the link is a bit hidden. Okay, so going from the hypercube to the cube doesn't make the structure so apparent, but let's make the structure really apparent, which is by doing extension, and this will be done on a set of product measures. Okay, so it's a bit complicated at first. So we're going to consider distributions on xi. So xi will be an interval. Okay, so if you define a probability distribution on an interval, you can define this cumulative distribution function. So here I have to reverse it. So I'm sorry for the probabilists in the room, but if I want to make the link exact with the binary case, I have to reverse the CDF. So now I define the CDF. Typically, the CDF at xi is a measure from minus infinity to xi. Here I take the reverse. I take the measure between xi to infinity. Okay, so in the plotted in 1D, if in dotted you have the PDF, so the density of xi, this is like the cumulative distribution function, which always goes from 1 to 0. It's always decreasing, okay, because this is taking the measure of smaller and smaller sets. So when xi is infinity, you get the measure of the empty set, so you get 0. And when xi goes to minus infinity, you get the measure of the full set, you get 1. Okay, so this is the usual like CDF setup. You go from the density in dotted to this cumulative density function in plane. And you can define this inverse CDF. Okay, so since this is like a decreasing function, you can define like an inverse also in not a real inverse, because this is not always strictly, this is only strictly decreasing if you have no atoms, but you can always define an inverse, which is left or right continuous. I always forget, but choose the one that you like, and this is to be true. All right, so once we have this, we can define our extension. Okay, so let's do it. So now we start from, we take a product measure. So we start from, we have n variables to start from. For each of those, we define like a unique measure on that set. Okay, so we get a product measure, and I'm going to define the extension like this. I'm going to take a t uniform in 0, 1. Okay, so this like the integral means that you take t uniform in 0, 1, and in fact it's going to be easier like this. You take t uniform in 0, 1. Okay, so you take a set there. So yeah, like here I have three distributions. So I'm taking n equals 3. I take so this is the inverse CDF, decreasing functions. I take a random t between 0 and 1. Okay, I take the when I hit my CDF, here this gives you like the inverse CDF function. This gives me the inverse CDF for the second one, and the inverse CDF for the third one. This gives me like for every I a value xi, and I take the submodular function taken at that value, okay, and I take the expectation. Okay, so here, so let me start again. I represent each of my variables as a measure. Hence, I have a CDF. And from the inverse from the CDFs, I can, for any threshold t, this gives me like a value on my original set. And then I can take the submodular function there and take the expectation. And this is exactly what the Lovász extension is. So it's not obvious at first, but this is essentially what's happening. The Lovász extension was defined in such a way. The only difference is that since we had a set with two values, the formulation is a bit different. Okay, so now I have something very nice. And also, I can compute this easily. So if you give me some measures, okay, this expectation I can compute easily, either by sampling or by just like, if, and this will be the case in practice, if that f of mu is piecewise constant, so if my measures are discretely supported, then I have a piecewise decreasing, piecewise constant function. And by sorting all of the elements, I can compute this in closed form in very much the same way as for the Lovász extension. Okay, so this gives me one nice extension. So why extension? Why? Because if I take Dirac's, okay, so now if I start from Dirac functions, okay, so I have n Dirac's, this means that the inverse, the CDFs are just like step functions like this. I have 3 step functions, and if for any value of t, for almost any value of t, I will always get the exact same value for my inverse CDS. Those are the locations of each of the Dirac's. Okay, so hence, when I take this expectation, it's almost surely equal to x1 xn. Hence, the value of small h is exactly the value of capital H at x1 xn. Okay, so by design, this is an extension. All right. So now, I need to put convexity back into the game. Okay, so here, that one can be defined for any functions. Like being submodular is irrelevant. You can always define this. It is like the Choquet integral. You can always define something like that. Okay, so now I'm going to use something a bit like related with convexity, which is called the convex closure. So again, for any functions defined on the set, you can always define a convex closure. And the way to do it is by simply doing convex relaxation. So here I'm taking like a cube with 4 points. So if you want a function which is convex, which is like less than the red points for any element of 0, 1, 1, 1, 1, 0, 1, 0, 0, you want it to be less than the red points. So we want to be convex, less than the red point as the given values, like as the given like arguments like this, and you want it to be convex. And that function is called the convex closure of your function. So this is the largest convex lower bound, and this is always, you can always define it if you start from capital X, which is a vector space. And a nice property is that minimizing a function and its convex closure is totally equivalent. Okay, so this shows in a sense that all problems are convex. So it gives me any optimization problem on the vector space. It's always convex. Why? Because I can simply define the convex closure, which is convex, and hence, if I can minimize this convex closure, I have like a convex formulation for my problem. So there is a big catch in that sequence of argument. It's all true. Okay, you can always reformulate the problem as being convex, but the issue is computing H tilde is as hard as solving the problem which you started from, in the sense that it's convex, but you have no access to any subgradient of that function. Okay, so you know it's convex, but you cannot do much about it. And the goal, as you will see in a moment, is that in our situation, that convex closure will happen to be easy to compute. Okay, but before that, we need a way to define that convex closure. And now you have to take the usual like brute force approach to compute convex closure. You have to do like a Fenchel by conjugation. So here, so define the function A, which is equal to h of x if you are a Dirac, okay, and infinity otherwise. Okay, I'm only constraining my function to have specific values at the given points. So for every Dirac, so remember I want to define a function of all product measures by imposing that it is correct or as close as possible to h of x of the Diracs. So I'm defining A like this, okay, and now I can simply compute the biconjugate, and I'm done. Okay, so I will spare you the details because this is like a few lines, but it's getting late, and I'm getting hungry. And so this is the way. So it's just simply like a classical exercise in convex analysis. So if you take a convex class, this is what you're going to do at one point, and you define the convex conjugate, do some computation. Okay, step 1, and then you take the biconjugate. So you take the conjugate of the conjugate, and then at the end, and I will really spare you the detail to get something, boom, like this, which is that function. Okay, so believe me, and I don't want to spend like too much time on this. What you obtain is that to compute this like convex extension, then you have to take the infimum over all measures. So you went away from product measures to full measures. So this may not be a product measure. You consider the expectation of your submodular function, h of x, but you need to link it with your product, with your measures mu1 to mu n, And the way to link it is by simply considering the fact that the marginals of your full measure are the ones which you started from. Okay, so this is, again, I start from a set of measures mu1 to mu_n. This is going to be where I'm going to optimize. This will be the variables I will optimize on. And I want to define, I can define this like convex extension, a function of mu. Okay, and for that, I have to solve this infimum over all measures, full measures, with given marginals. Okay, so this should start to ring a bell. And this is essentially, so the result over there, is essentially optimal transport. Okay, so here, my task in the next 5 minutes is to review like 20 years of optimal transport in 5 minutes. So this is going to be a bit difficult. So I'm going to go be very brief, and I can refer you to books later on. So what is the problem of optimal transport? So who has ever seen optimal transport? Ever or never? I think I see someone in the back I know who know optimal transport, and they say yes, but I say never. So I say I switch in the middle. So who knows about optimal transport? Okay, good. All right, so the optimal transport, this is like a topic they can get you to the Parliament of France first. So it's very important, a very important topic. And so the thing is, so you start from the simple problem of, so you have two measures, mu1 and mu2. And you started from practical problems. Okay, you have some sand over there, which you want to put over there. Okay, so you have to carry it yourself. So the goal is to minimize the amount of pain which you have to suffer to transfer the sand from there to there. And so if you take the distance between this point and this point, you want to minimize the average distance between this and that. But of course, you cannot like create or remove sand, so you have to preserve the measure, the total measure. Okay, so this is essentially called the Earth mover distance, and this dates back from Monge. And yeah, so this is like the optimal transport problem. And one nice way, so this does not exist always, but there's a nice like relaxation by Kotorovich, which instead of trying to find a map from there to there, is formulating the problem on the space of product measures. So you take your two sets, okay, x1, x2. You define a joint measure gamma. You want to find like marginals to be correct. So you want to prescribe marginals, and you want to minimize the cost, the average cost of that. So the link between the two is that if you usually solve that one, okay, and you take the support of this joint measure, often this will be supported in a very only on a single curve, which will be the map from x1 to x2. Okay, so here clearly, I don't want to spend too much time on that. It's just you can find optimal transport defined in that way. Okay, and so this is a Kotorovich formulation, and this has very nice properties. It's often referred to as the Wasserstein distance between two measures. And if you want to know more, do look at the book by Cedric Villani or the book by Santor Boggio, and to know a bit more. So the way we're going to use optimal transport there is rather obvious. It's rather through this extension to multiple marginals. So if you go from 2 to n, okay, so this is a usual extension there, and you can minimize the expectation over a full measure with prescribed marginal, and this is just like optimal transport. Okay, so here this is a summary in like 4 minutes of like 2 big books. Okay, and if you want to know more, I really those books are available. All right, so now to summarize, we have 2 views. Okay, so we have the view through the CDFs, where you take like you take a random t. So let me go back to that view. You take that one. Okay, you take a random t, and then you take values of h after you take the inverse CDFs. So this is the first view, and we have the second view, which is this one, which is convex. It's a convex view. So the first view, it is closed form. It's nice because give me a value, give me some mu's, and you can compute the extension, but it may not be convex. The second view is the opposite. It's always convex, but you can almost never compute it. And the beauty of this is because of submodularity and because of non-results on optimal transport, those two views happen to be equivalent. Okay, so here, for the moment, here, I've done nothing. I've just reformulated the problem. I've defined two extensions, and now this is where submodularity comes in. And why it comes in from a very nice result by Guillaume Carrier, stating exactly what I wanted. The convex closure is equal to my extension. Okay, so if you take like that result from optimal transport theory, it translates to the fact that if I start from a submodular function, those two extensions are equivalent, and hence this one is convex. Okay, so or this one can be computed in closed form. So you can see this in two views, and this is essentially the main contribution of that work is to realize that those two are equivalent, which is just using that theorem from Carrier. The proof I will skip, but I think if you want to remember a single thing from optimal transport, if you start from one-dimensional distributions and with a submodular cost, you can obtain it in closed form. Okay, this is really, for the optimal transporter, this is really like a trivial problem. Okay, this is a case where there's nothing to do, but for us this is the nice case because this ties nicely submodularity with convexity. So now, let me skip that. And now we're done because what we can show now, because of that link, is that my function is submodular if only if the extension is convex. Okay, this is just applying this optimal transport result. We can show that minimizing the submodular function on the set is like doing this like convex optimization problem. So this is exactly the same result as before, but we went from the hypercube to the all potential intervals. And even better, and I've not described this so far, but you can compute a subgradient of H. Okay, so you can optimize this easily. Okay, so this is essentially the exact same slide as before, but we have now an extension from this was the set 0, 1 with two elements, and now this can be any interval. And again, the only like thing that we have used is the fact that we have like totally ordered set on which you can define an order and define submodular functions and so on. All right, so this is like what we obtain. So first, okay, a big disclaimer. This is not the first time people have realized that you can minimize submodular functions. Okay, this was known from before because you can reduce it. You can reduce it to a binary function by using a clever trick. But here we provide a direct link, and also it's more efficient in practice. For reasons I don't want to describe, but it's more efficient in practice. All right, so let's look now for the last 5 minutes how I can minimize the functions. And this is rather obvious. So first, I will discretize the sets to be for simplicity. And also this is the most efficient algorithm so far. And so here, it is not discretizing the full cube. So I'm taking like a product of intervals, and I'm considering an exponential number of points. Okay, I take every interval, I cut it into k pieces. Okay, so at the end, I'm never exponential in n. I'm just like a polynomial in n. So I discretize all sets like that. Okay, then I'm assuming a typical regularity condition for functions. And at the end, what you obtain by applying the simplest algorithm, which is like projective gradient descent, you obtain like a complexity, so which is like for the expert in the room, you get this 1/root T complexity. This is like the complexity, the convergence rate of subgradient descent. This is just the Lipschitz constants. And since every iteration has its linear time almost in n and k, you get that if you optimize over the discretizing grid, you can optimize like any continuous submodular function at precision epsilon with a complexity of that kind, like n cube over epsilon cube. So for the expert in the room again, if you have convexity, you get epsilon square, and here we only get epsilon cube, and it's not totally clear if you can improve over that or not. Okay, so this is, so here the way it is done is simply you take your function here, you map it into this product measure, do subgradient descent over there because this is a convex problem, and map it back at the end. So let's see an example. let's forget about that. So you see like a very, this is like a link with sparsity. Let's say you want to solve that problem. Okay, so you want to minimize the function x. So it's -1 to the -1 to the n. So you have n values in the -1, 1. Okay, and you have a problem where essentially you have like a noisy signal, which is in black, and you want to denoise that signal, and you want to make you have the prior information that that signal is smooth and quite sparse. So you have values which are close to 0 over there, but you have some, also you want some smoothness over there. Okay, so the red curve is what you started from, and you observe the black values, and you want to recover the red from the black. So what you can do for that is to design a simple least square formulation. Okay, so z is what I observe, and I want to make to be close to z. Okay, so least square loss. Then I can add some sparsity. Okay, so you will see that a lot this week. Like the sum, when alpha is 1, you get the L1 norm, but alpha can be less than 1. And you want to add some smoothness, so you add some like smoothness prior, where you penalize for any pair xi plus 1, you penalize the distance between xi and xi plus 1 square. Okay, so this is doing what you would like to do. You feed the data, you put some sparse prior, and you put some smoothness penalty. So you may think he spent like 1 hour dealing with submodularity, and he's showing us a convex problem. No? Who think that? No? Ah, thank you, Pierre. Yeah. Okay, so it's convex because this one is convex. Okay, this one is convex. This one is also submodular because this is separable. This one is also submodular because this is like a convex function of a difference. But this one, okay, so this one is convex only if alpha is 1 or more than 1, greater than 1. Okay, but it's known that if you use like the L1 norm alone, this may create some extra bias effect, going to shrink a bit too much. And if you use alpha being closer and closer to 0, you're going closer to the L0 quasi-norm, pseudo-norm. But here, it's not convex, but it is still submodular. Why? Because it is separable. So here I can put the alpha that I want. I can put alpha being 0 if I want to. I'm allowed to do that. Okay, because this is still submodular. Okay, so this is what you obtain when you can minimize that function. So you go from you recover the blue curve, which has indeed a sparsity effect, but no shrinkage effect due to the fact that I have an L1 norm over there. So here I use alpha, which is 0.2, I guess. I forgot, but it's a small alpha. So in terms of convergence rate, okay, so here, and this does generalize to many other like proximal operators. So why? Because proximal operators are nice because they have often some like separable structure, okay? And as soon as you have as soon as the non-trivial part is due to submodularity, and this was due here, that the smoothness constraint was like a submodular function, then you can do similar things. And then, okay, let me skip this and conclude. So here, so in this talk, I've tried to present like extend known results from submodularity from binary functions to continuous domains. And this was done by defining an extension to product of measures. And here, the reason why I enjoy doing this is that with 0 line of proof, just reusing a known result from optimal transport, I can recover like 20 years of submodularity and highlight the key property, which was really like the optimal transport is in closed form for those problems. I've shown like some simple application to decompute the proximal operator for a non-convex regularizer, but there are also other ones. So in terms of ongoing work, so there are a lot of things to be done. First, can be used as same like optimal transport link beyond submodularity. So this is something which I've been unsuccessful so far, but this is, I think, interesting. Trying to improve on this epsilon cube. Okay, so this, we have had more success, and I think we went from epsilon cube to epsilon to 2 plus 1 over q, where q is the order of smoothness of your function. Okay, so it's not 2, but it's 2 plus 1 over q. And if your function is very smooth, you get close to 2. You may want to go beyond minimization. So this can be, this is often many problems when you look at submodularity are naturally cast as being maximization problem. Okay, so tough luck, this does not apply, but other people have already extended this to maximization. And then you may want to consider mixing the two sources of polynomial time. I have convex functions, which can be minimized in polynomial time. I have submodular functions, which can be minimized in polynomial time. Maybe the sum of the two can be minimized in a polynomial time. And no, that's not true. At least I'm not aware of this being possible. And I guess you can cast like NP-hard problem like this. So I guess this is not going to happen anytime soon. And finally, if you're like, let's say you want to do image processing. Okay, you have a cut, and for all of those problems, like relying on like the low-pass extension is a bit hard. Why? Because you always get like complexity of this kind, 1/√t. So if you want to get a very high precision, and this is true when you do graph cut, you really want a high precision for your small structures. So this means that you need like, unlike machine learning, you want the precision to be very high. So epsilon has to be very small, and t has to be very large. Okay, so those like first order techniques for that problem do not work. And what we have done for that is to use like different types of structure. For example, if you get a graph cut in 2D, this can be seen as a sum of the graph cut for chains which are horizontal and chains which are vertical, which is a classical decomposition. And there you can use submodularity to be competitive and apply all of that to very large problems. Thank you for your attention.
Questions for Francis?
Can you go back to the simulation results?
Yeah.
Yeah, so here I was wondering why exactly 0.2 for alpha? And the second question is, would you say alpha is related to the sparsity rate of the signal?
Oh, so you should ask a question to the expert in the room on sparsity. So alpha here, so we take alpha equals 1. The result will be the exact same thing, but shrunk towards 0. Okay, so it is known that the L1 norm has a shrinking effect, which is like removed if you take alpha being less than 1. And the smaller the alpha, typically the less shrinkage you get. So here I took alpha being 0.2 because I want it to be far from 1, but not 0. Because at 0 I lose continuity, and then it's harder to optimize. So I took the smallest possible value, which was not giving me any like shrinking effect and still continuous.
Yeah, when you show that the submodular problem is equivalent to optimal transport, which one of those is the simpler one, the one that you apply gradient descent to? Oh,
so at the end, okay. So if you go back here, okay, so we have this equivalence, okay. We need this one to show convexity because this is like a jointly convex function in gamma and mu, okay, and the infimum over gamma is a convex function of mu. So we know it's convex because of that, and we know how to compute the subgradient because of this, because this one is closed form. And this is exactly the same thing as in the binary case. We just use this one to make sure you're convex. So if you believe in non-convex optimization, you can like go straight and minimize that one directly, but you wouldn't know in advance that you would converge to the global optimum.
Okay, thanks.
Is there another questions for Francis? No, so I think we'll thank Francis for his talk.